And then coming to the continuous data, they similarly have a formula for Z, and all these are just the approximations. So you can say L plus Fm minus F1 divided by 2Fm minus F1 minus F2 into C. So here also we do the same thing. So we have class interval, we have frequency, and most repeated value will have the highest frequency. So we take the highest frequency and we call it as Fm, and the respective class interval, lower limit and upper limit, gives you that. So you have the value of L, lower limit, and Fm indicates the highest frequency. Its previous frequency is F1, its successive frequency, the next frequency is F2, and C is the class width of the identified modal class. So this is called as the modal class. Modal class indicates the class interval where the mode lies. How to identify modal class? Modal class is the class with respect to highest frequency. Now often we say mode is ill-defined because at certain distributions you will observe there is no mode. For some distributions you will observe multiple modes, and hence, so in those cases, when you want to obtain the value of mode for a distribution where mode doesn't exist or where multiple mode exists, so whenever there is no z or many z, we will have a dilemma in picking a particular value of z. So in that case, we can use the formula that mode is equal to 3 median minus 2 mean, m for median and x bar for mean. So in that case, what you have to do is you have to obtain the value of median, you have to obtain the value of mean, and using that you can obtain the value of mode. So these are the three basic measures of central tendency which are very vastly used. And why we have many measures? Because based on the type of the data, based on the situation or the characteristic, we would like to use the particular measure. Now, of the cases, X bar is the most widely used measure because for all the variables, all sort of variables where you have the continuous variables or variables measured in terms of interval ratio, interval scale or the ratio scale or even the ordinal scale, we could use our X bar. But the problem is this, your X bar is based on all observation. This is one of the merit. It uses all the values of X or all the observations. So if your observations are extreme, that is contains very abnormal values, our X bar gets affected by the abnormal values because they are based on every observation. So what I'm telling is you have certain set of data and much of the observations what you are observing are present here in the lower part of this population, but there are only say one or three observations which are present in this case. So we could somehow divide the given data set into two parts. So one where all the values are close, the other one where they seem to doesn't fit into this particular data. So they are said to be extreme values. So they are the values of x may be written wrongly by human error or maybe because they have come from the sampling errors, or it could be correct values only but they seem not fit to this data. So in that case, what happens is instead of observing the value of x bar here with respect to this, we observe somewhere here in between these two data. So our x bar is neither giving us the clear picture regarding this as well as this. That is the reason. What we mean is it is affected by the extreme values or abnormal values. So what we have to do in that case is you have to identify whether they are truly abnormal values or extreme values, and if possible you eliminate from the data. Now elimination in the data points always helps us in losing the observations or losing the characteristics of the population. Each and every data point, whether it is small or large, observed on the variable x indicates or uh, it captures the characteristic of that particular population. It has enough information regarding the value of x. So if I say there are three observations which are extreme or there are four observations which are extreme, and if I'm removing them from the data, I'm using some information regarding the values of x. So that's why I often say your n should be very large in order to come up with the values of measures of central tendency as well as to generalize them, so that in the larger values, if you remove some extreme values, there will be no loss in the data. Now, how large our n should be, how to identify these extreme values, that will be looking in the coming sessions. Now, coming to the important properties of arithmetic mean. So we say arithmetic mean is that number such that it satisfies this property. That is, if you take the total of deviations of your observations from its arithmetic mean, that will be equal to 0. So once after computing your arithmetic mean, take the total of the deviations from x bar. So what I'm telling is you have some x, say I have 2, maybe 3, and 6. So these are the observations. So the mean for this distribution is sigma x by n, which is equal to 14 by 4, right? So it's 12, 13, 14 by 4, which comes to 3.5. So now what you have to do is observe the difference of every x from its arithmetic mean. So the arithmetic mean is 3.5. So from every x, I subtract 3.5. In the first case, I'll get 2 minus 3.5 minus 1.5, 3 minus 3.5 minus 0.5, and 6 minus 3.5, which comes to 2.5. So when you look into the total, you will observe that as 0. So it is the total of x minus x bar. This happens only with respect to arithmetic mean. Now, other than x bar, if you take any other value and check the differences, the total doesn't come to 0. So you can take geometric mean, you can take mode here. 3 is repeated twice, so I could say z is equal to 3. Now subtract every value of x from z, which is our 3. So I'll get 2 minus 3 minus 1, 0, 0. 6 minus 3 is 3. Total comes to 2, which is not equal to 0. So apart from this, take any other constant. Say instead of 3, I'll take the constant 4 or 2. Obtain the deviations. Again, you will observe the deviations to be non-zero. So you're getting minus 1 in this case. So what we mean is arithmetic mean is a special value such that if you take the total of the deviations from x bar, that will be equal to 0. And if you want to examine the same property with respect to a frequency distribution, then we say f into x minus x bar is equal to 0. So what we do is, so you have to obtain x minus x bar, and in this case our x bar is total of fx divided by total of f. So you have been given with the distribution of x and f. So compute fx and obtain the arithmetic mean using the total fx and f. Then you subtract x minus x bar, do f into x minus x bar, and you will observe that the total is equal to 0 because f indicates the number of repetitions. So you have to obtain the repetitions for x minus x bar, then only you will get the total 0. So this is the first property of arithmetic. Now if you look into the second property, so if you obtain the total, so this is somewhat called as error. So if you obtain the squared differences, squared deviations or the squared distances from x bar and its total, that is always minimum compared to any other such measure, any other such measure. So instead of taking your x bar, take median, take z, etc. And if you look into the square, we call this as minimum. So we use this in defining the average distance between x and x bar, and that measure is commonly called as standard deviation or variance, and this is called as the root mean square deviation. So obviously we will be taking the square root in order to make the units of measurement same. So let's take the same example and see how it becomes minimum. So I have x is equal to this. So I had x minus x bar was 3.5. So I'll take some a is equal to 2 and z is equal to 3. So x minus x bar was minus 1.5 minus 0.5 and 2.5. Now when I obtain x minus x bar whole square, so we get 1.5 whole square, 2.25, 0.25 and 6.25, which comes to a total of 9. Now observe the same measure x minus x bar whole square by changing x bar and replacing it by a value called as a. So I'll directly do that x minus a whole square now. X minus 8. My x is 2336 and a is 2. So I'll have 2 minus 2 whole square, which is 0. 3 minus 2 whole square, 1. 3 minus 2 whole square, 1. 6 minus 3 whole square, which is 9. So the total is coming to 11. So just look into the numerical value of the total. Now instead of 2, if you take z and obtain x minus z whole square, then you will have 2 minus 3 minus 1 whole square is 1. 3 minus 3 is 0. 0 square is 0. 6 minus 3 is 9. 3 square is 9. Total comes to 10. So replace your x bar by any other number, then the total will be larger than this. Therefore, we say sigma x minus x bar whole square is minimum. In case of frequency data, you will have sigma f into x minus x bar whole square as minimum compared to any other such measure. So this is the second important property of mean. So the square deviations from mean is always minimum and the total, or further you could say the average of that, is also minimum. Third property is called combined mean property. So this helps us in obtaining the mean of certain groups of observations where the group means and standard deviations or maybe the sizes are known. So what we have is, so I have say groups here with size n1, its mean is say x1 bar. You have another group size n2, x2 bar. Now you want to combine this group n1 and n2 into a single group with observation say n1 plus n2. And now if you say what will be the mean of such distribution, then that could be easily obtained just by the information on our n1 x1 bar, n2 x2 bar and so on. So the same formula could be used. So this is the formula n1 x1 bar plus n2 x2 bar plus n1 plus n2, and if you have k such groups, so you could say a combined mean of all the groups of observations, k groups combined together will be equal to this. So why do we need this formula is that without knowing the actual values of x of the observations, we are obtaining the value of mean. So observations gottilla. We know the information regarding your group means as well as the group sizes. You could just compute the mean using the information. How this works is logically we are talking about our sigma x by n. So mean is defined as total of x divided by n. So from the first group, so if I say the mean is n1 x1 bar, so in the first group x1 bar is nothing but sigma x by n. Even in the second group, our x2 bar is nothing but sigma x divided by n2 there. So if I combine the observations, so in the group 1 I have n1, group 2 I have n2, therefore the total observation becomes n1 by n2. So for the computation of mean in the denominator I need the total of observations. So n gets replaced by n1 and n2. In the numerator I need total of x. So I have combined all the observations. So total of this set of observations is same as total of this observation plus total of this observation, and from this our sigma x is n1 x1 bar and sigma x is n2 x2 bar. For the computation of mean, I need the total of both. So it will be n1 x1 bar plus n2 x2 bar. So that is the logic. So these are the three important properties of arithmetic mean. So let us look into some numerical problems on obtaining AM as well as median and mode, and then we'll look into the next set of measures. Now this combined mean helps you in obtaining the ratio of two groups when you know the means. So if you have the cases where you have the observations on group 1, you know the combined mean, you want to obtain the mean of the second group, that case you could go so. So you have the mean marks of students of a class, the mean marks of boys, the mean marks of girls, what should be the ratio of boys to girls in that class. All those questions are answered using the property of the combined mean. Let us take some raw data and see how to compute our x bar, z as well as m. So let me take some x values like 20, 21, 18, 19, 15, 1. Okay, so these are the values of x. So I have a total of n is equal to 12 observations. So my mean x bar is given by the formula total of x divided by n, and then z for raw data is most repeated value, and m is equal to middle value in the arranged data. So first you have to arrange the data to obtain the value of mean. But for mean and mode, you could just look, observe, and write. Now there are many repetitions here. Of the many, 20 is repeated for a excuse me, 20 is repeated for 3 times. Therefore, z is equal to 20 is the mode for this distribution. Now, if you look into the total of x, so we have 20 plus 21 plus 18 plus 19, 16, 15, 20, 18. We have 19, 16, 20, 21, which comes to 223. So 223 divided by 12 is equal to 18.583. So if you have any unit of measurement, so let me say these are the maybe length of fish observed, maybe in the rounded values close to inches. So every measure will have the unit inches. Now to obtain the value of median, you have to arrange the data in the increasing order, and that arrangement is called as array. So we'll start from the lowest value. I have 50. Write all the repeated values. Don't leave any number. All the 12 observations must be in your arrangement. 16, 16, then we have 18, 18, 19, 19, 20, 3 times 21, 2 times 2, so then 12. Now coming to the middlemost values here, so have the two middle numbers which are 19. So average of that is also 19. So median is equal to 90. So that is how easily you could pick the value of median for a raw data. Okay, coming to the situations, why do we need different measures? So for this data, whenever we talk about some data which are obtained in the interval scale or the ordinal scale like this, arithmetic mean is sufficient provided there are no extreme values. If there are many extreme values and if you could not remove the extreme values, then the suitable measure are the middlemost value, which is median. If you're talking about data like this, integer points only, several repetitions only, less possible values, like say the range is somewhat 15 to 21, within 15 to 21, many values are getting repeated, then you could say the suitable measure there is small. Of course, your n should be large in that case. Now, there are cases where arithmetic mean cannot be easily applied. So, as said, the common measures are where the data is repetitive. So, when we say data is repetitive, like say for example, qualitative data. So, if you say in a group of people, so you are observing many people with say blonde hair or fair hair. In that case, you could say the measure is your Z, because for qualitative data, there are no numerical values, so obtaining sigma x becomes difficult. So x bar is not suitable. So Z and median is suitable. Median is suitable provided they could be ordered in an arrangement. There should be some logical order, say from low to high. So in that case, you could talk about median also for the qualitative data. But if you fail to establish which is lowest value, which is highest value in the qualitative data, then the suitable measure is Z. And when it comes to the variables like say shoe size or the ready-made garment or the dress size, so there, if you want to talk about the concept of average sales, then we talk about in terms of mode, because for these cases you cannot talk about the average sales in terms of median, in terms of the arithmetic mean, because here the sales may not be always with respect to x bar, because x bar need not be one of these values. So we know that the size of shoe may be starting from say 4, 5, 6, 7, 8, 9, maybe in special cases it will go up to 12 or 14. So these are the possible values. So of this we observe much of the sales occurring only in this particular zone. So if I want to talk about average sales, if I use the concept of x bar, I might end up getting answers like 7.1 or 8.9 or 6.2 inches as the answer. So which are not at all present in our production, and it is hard to interpret also. I cannot say the average shoe size is 8.9 inches. Round ಮಾಡ್ಕೊಂಡು ಹೇಳಕ್ಕಾಗಲ್ವಾ? No. So rounding concept is not at all used. Whatever the value you have to keep it like that. So instead of using arithmetic mean, because I cannot have the garments or the shoes produced with respect to these inches, so we better take the average as our Z. Why can't we use median? Because median somewhat divides the obtained values into two parts. So it is just giving you that value, which is dividing the distribution into two parts. But when we say look into the sales, so we look into the frequency actually, because as a store owner or the manager, I should always back up my number of items in the shops. So based on which particular value is selling most, I would like to keep up the stock up those values in my shop. So based on the frequencies, that's why we say in these cases the average suitable averages are either mode or median. So that's why we have defined several such measures. So even the concept of geometric mean and harmonic mean have come like that only. So we have cases of x where our x is in terms of rates or ratios or in terms of percentages and all. Then these ratios or rates or percentages at times they could be very low values or they could be very high values. The problem with X bar is that it cannot deal with the presence of high or low value along with the other data. It gets fluctuated or affected by that. So we use what called as the concept of harmonic mean and the concept of geometric mean when it comes to data like this. So if you're talking about growth rates of populations, growth rates of bacteria in the lab, etc., then we talk about the geometric mean. And if you're talking about data in terms of speed, distance, velocity, so we use the concept of harmonic mean, because the formula of our average speed or speed somewhat becomes same as the formula of harmonic mean. So in these cases, we'll be using those measures. We'll just take an example on discrete data. So when we say discrete data will be given with the values of x along with the values of f. I have to join back. I'll end this session.